Hello students, welcome to the session. Today we are going to discuss about sets, relations and functions. So what is a set? I had a lot of confusion in my student life when I come across this concept set. Most of the teachers, or maybe most of the books you read from, they say like set is a well-defined collection of objects. A well-defined collection of objects. A well-defined hota hi kya hai? So what is this well-defined actually? See, generally when we come across the textbooks, like they give examples like the stars in the sky is not a set, or you take a handful of sand, it's not a set. Then immediately it struck in my mind that okay, if there are many objects in that collection, then it is not a set. No, but right, because we know that set of natural numbers, set of whole numbers, these all are sets like which start from 1, 2, 3 and they go on, like there is no end, like there are infinite number of elements in it. Like I cannot say how many are there, right? But still it is a set. Then how come the set of means the stars in the sky, or maybe handful of sand, the particles of handful of sand are not as sets, right? Even whole numbers start from 1, 2, 3 and so on. So what exactly is this well definition, like well-defined collection of objects? See, simple. A well-defined collection is, see, whatever the numbers in this, like I'm marking now, these are called as elements. Okay, these are called as elements of the set. So the elements of the set, each element should have its own definition. It should be identifiable by itself. Say suppose I ask you to write 5. Would you write 7? No, you know clearly what is 5 and how it looks like and what number it is, right? So it has its own definition. If I ask you to write 5.5, it is still identifiable by its definition. So which you can define. Every element should be definable. Then it is called as a set. It can be of different types. Like I can have a set with alphabets and numbers together. This is also a set, right? Which are like identifiable by own definition, are called as is called as a set. So a set is nothing but a well-defined collection. Well-defined. I think now you understood what is well-defined. Well-defined is nothing but each of the elements, like each of the entry in that group, like we call it as a element. So each of the entry or each of the element in it should be identifiable by its own definition, right? Then it is called as a set. And these sets have equal sets we call. What is an equal set? So suppose I have a set A is 1, 2 and 3, and I have another set B 2, 1 and 3. So the elements in set A are 1, 2 and 3, and in the elements in set B are 2, 1 and 3. Both of them have equal number of elements, 3 and 3 in this. And the elements are also same, like 1, 2, 3 and 2, 1, 3, though the order is different. Here the order does not matter. The order may be anything, we don't even mind about the order. The element should be same. Every element, whatever element is there in A, it should be in B, and whatever element is in B, it should be in A. Then we call those two sets as equal sets, right? Now what is how do we measure these sets? Say suppose I have a set A is equal to 1, 2, 3 and 4. So what can I say about this set? Yeah, I can say that it has 4 elements in it. So we denote it with the n of A, which is called as the cardinal number of the set. Cardinal number of the set, which is equal to here 4. Right. So if there are more, like say suppose the set of natural numbers 1, 2 so on, the cardinal number of this set is infinite. This set is called as infinite set, and it is a set. It is not a collection of simple collection of objects. It is a set because every element, I can identify each and every element very easily. Right. Now what can you say about A and N? If you look at these two, what can we say about these two? Like A is 1, 2, 3, 4 and N is, if I write, like I can write all of them. Say I cannot write all of them though, but I'm writing to some extent to where I would like to, because I want to compare A and B. When I compare these two, if I look at A, all the elements which are there in A are present in N. So what can we say here? We can say that the set A is contained in set N, and this is written as a subset of N, or else we can also read it as A contained in N. This is called a subset. What is a subset? A is a proper subset, like it is entirely containing inside. So A is called as a subset of N, as every element of A is there in B. So to talk in terms of definitions, if every element of A is in N or else in any other set, then that particular set is called as a subset to this. For example, if I am comparing A and B, these are the two sets I am comparing, and if I have every element of A is in B, say whatever element I take A, say A belongs to caps A, then this implies A belongs to B, then this means that A is a subset of B. Means what? For all elements in A, that element is again there in B, then A is called as a subset of B. Right? Say, suppose I have A is a subset of B. Right? Means what? A belongs to A. This implies the same A belongs to B. Let us say this is 1. And I have at the same time B is subset of A. What does this mean now? Like say suppose some X belongs to B, then what does this mean? This X is again there in A. So whatever element is there in A, that is there in B. So I should have A, B, C, and maybe some other elements if there are, but the next condition says every element of B also is there in A. That means there are no other elements here, because if I have D in the set B, then you will get the same D in A, but there is no D in A, then our second condition will fail here. So if A is a subset of B and B is a subset of A, then what does this mean? This means that A is equal to B. Then we call these two sets as equal sets. What do we call them as? Equal sets. Say suppose I have a set C which has X, Y and Z. Right? X, Y and Z. This has 3. See, this is number of elements in A is 3. Here number of elements in B is also 3. And number of elements in C is also 3. But the elements are different. So C is a subset of neither A nor B, or A and B are also not the subsets of C. But what can we say about these three? If you observe carefully, these three have equal number of elements in them. So I can say A and C are equivalent sets. Similarly, I can say B and C are equivalent sets. So the sets which have equal number of elements in them are called as equivalent sets. Now, if I see, as we have seen just now, right, like A is A, B, C, and say I have C as X, Y and Z, and say I have B, another, I'm taking a different set now, like B is not the set from the previous example. Let us say this is 1, B and Z. This is one more set. If I look at A and C, these two are called as disjoint sets, because there is no common element in between them. Like A and C are entirely different, like you don't have at least one element in common with them. These are disjoint. But when I look at A and B, I cannot say that A and B are disjoint. They have an intersection here, which is the element B, which is there in both of them. Right? A and B are not disjoint. A and B are not disjoint. At the same time, C and B are also not disjoint sets. So the disjoint sets are nothing but the sets which have elements no elements in common. I'm sorry. So which have no elements in common are called as disjoint sets. And when I am talking about, say, I'm talking about sets like A is 1, 2, 5, and B is, I'm talking about, say, 3, 7, 8. These are the two number sets I'm talking about. Or else rather we'll say E is a set of all even numbers, say 2, 4, set of all positive even numbers like 2, 4, 6 and so on, and O set of all odd numbers like 1, 3 and so on. If I talk about these two are the sets given to us. Then if I talk about a set of natural numbers, what will it have? 1, 2, so on, all the numbers. So now when you talk about these two sets, natural number set is called as the universal set with respect to this even number set and odd number set. So universal set is nothing but the set that comprises of all the sets which are under consideration. Say suppose I'm talking about prime numbers also, this also fall in this, right? But if I talk about integers, say suppose I'm talking about negative numbers, then my natural number set wouldn't be my universal set here. Then I should go for the set of real numbers, right? So it depends upon the universal set we talk about depends upon the sets we consider to operate on. Like if you are operating on even positive and negative numbers, then your universal set becomes like set of integers. And if you are dealing with decimals, rational numbers, irrational numbers and all other stuff, then your universal set will become real numbers. And if you are talking about the imaginary numbers, say suppose like the negative square roots, or maybe get into complex numbers, then your universal set will become the set of complex numbers. It depends. Like suppose if I am talking about only these two sets A and B, then my universal set I can simply say numbers from 1 to 10 is my universal set. I can always say that because I am talking about numbers from 1 to 8 only in this one, right? Even though I am missing few of them in the middle, but universal set will be 1 to 10 to be on safe side. Right? A universal set is nothing but the set which comprises of all the sets, which has all the sets as subsets to it, which are under consideration for that particular scenario, right? Then see, we have seen about universal set. Now if I ask you, say suppose we want a number, a real number, whose square root is, or else I want a real number such which is equal to square root of -4. I'm saying this is a real number. Okay, let me say small a. This is a real number which is equal to -4. I am asking you to write a set of numbers of this one. Like, can we write something? Right? It's not possible. The negative square root is not a real number. So when there is a set where say suppose I'm writing x such that x is both even and odd. How many elements do I get in this one? I want an element which is both, I want a number which is both even and odd. How many numbers will come in this one? No numbers. So this type of set, there is nothing in this, but still it is a set. This is called as a null set and it is denoted with 5. So why do we use it? Where do we use it? We'll learn when we are doing some problems on them. So a null set is nothing but a set which has no elements in it. That is, the number of elements in this, the cardinal number of null set is 0. Even if you write 0 inside this, then it wouldn't become a null set. Suppose if I write like this, this is not a null set, guys, right? So you cannot say that this is a null set. I hope I'm clear so far, right? Now let us see. I have a set A is equal to 1, 2, 3. We have seen what is power set. What is a subset, what is a universal set, what is a null set. Yeah, and one thing I forgot. See, suppose A is a subset of B, right? A is a smaller set. Like this is B, if you say, and this is A. Then we can also call that B is a superset of A. B is a superset of A, right? That is, B contains A. Here A is contained inside B, right? Now when I have A here, so can you tell me what all will be the subsets of this set? So you will have null set. Null set is a subset of every set. Nothing is a subset of every set, right? And A itself is also a subset of it, right? And then 1 is a subset, 2 is a subset, 3 is a subset, and then 1 comma 2 is a subset, 2 comma 3 is a subset, then 1 comma 3 is a subset, right? So if you write all these in one set, that is called as the power set of A. What is this? The power set of A is nothing but set of all the subsets, all the possible subsets of the given set is called as a power set, right? So it's nothing but all the subsets, all possible subsets. Like here I have 1 2 3 4 5 6 7 8 subsets I have, right? The set of all possible subsets, and it can be easily found by using this formula, like 2 power n, where n is nothing but the number of elements in it. So 2 power 3 here is 8 subsets you get. Like if you have 4, then you will get 16 subsets, and it will be tedious job to write. That's why I took a small set here, 1 2 and 3. So whenever you have a set, if you want to know the number of subsets it has, or else the number of elements in a power set, n of p of a is nothing but the cardinal number of the power set, then it is simply 2 power n, where n is the number of elements in the actual set. So a power set is nothing but the total number of subsets. The set of all subsets is nothing but the power set of the set, right? So now we know what is a power set, what is subset, what is universal set, and what is null set. This all we have learned. Now there are some operations defined on these sets, like how we do addition, subtraction on numbers. On the sets also there are some operations defined. I think you all know about these. One is nothing but the union, and the other is nothing but the intersection, right? So you write A union B is nothing but the total, all the elements, they may be either in A or in B. If you want in numbers, like 1 2 and 3, and I have 2 3 and 5, then this is A and this is B. My A union B will be equal to 1 2 3 and 5. You won't repeat the numbers, but you will write all the numbers which are there in both of them together. And A intersection B is, the diagram wise, is this one, like you shade the common area, and A intersection B in the set wise, if you talk about the common parts, here 2 and 3 and here also 2 and 3, so 2 comma 3 are nothing but the A intersection B. Right, so A union B we sometimes call it as A join B, like where A and B are together, like they are joined together and the numbers are taken. This is called as A meet B. This is read as join and this is read as meet. Okay. And then we have seen like what is a universal set. Say suppose I have a universal set of natural numbers and I have a set A as 1 2 and 3. This is set A. Now I want something called as A complement. A complement is nothing but everything in the universal set other than the set you are considering. So if you complete the Venn diagram, it looks something like this. Like you won't shade A, but everything else you will consider. And you can also say this as natural numbers minus A. A complement is natural numbers minus A. Generally universal set we represent with U or else mu. Either U or mu you use. So A complement, generally when someone says A complement, it might strike in your mind that it is U minus A or mu minus A. It's the same thing. The universal set, whatever you consider, you have subtracted from there. Right, now we have learnt what is A union B and what is A intersection B. Right, now there is something called as symmetric difference. First, before going that, let me tell you how we find the difference of two sets. Say suppose I have A as 1 2 3 and 5. I have a set B 2 5 7 and 6. Right, these are the two sets I have, and I want to find A minus B. So what is A minus B? So from A you have to take away B and write the remaining numbers or remaining set of the set A, not B. So here when you look at this, I have 2 here and 5 here. So I remove those and I write 1 and 3, but you don't write 7 and 6. That's called as A minus B. And if I say B minus A, I think you might be guessing it by now. So it would be when you subtract 5 and 2 from that, so you only have 7 and 6. And if you look closely, A minus B and B minus A are disjoint sets. Right, they don't have, like if you are doing a Venn diagram, if this is A and this is B, I want A minus B. From A I subtract B and take the part whatever is there. and if it is B minus A, so I shade only B but not A. Right? Now if I find A minus B union B minus A, this is called as the symmetric difference of the sets. Like if they'll give you simply two sets and ask you to find the symmetric difference, you just need to find A minus B and B minus A and their union. So that would be nothing but this one, like A minus B union B minus A is two shaded parts together taken is called as the symmetric difference of the two sets. Even with the numbers also you can do the same and you can find the set. Right? So what is symmetric difference? It's nothing but the union of the difference of the two sets taken one at a time, like A minus B union B minus A. Next, the Cartesian product of sets. Like so, okay, we have learned how to join two sets, how to find the intersection, the meet of the two sets, and how we also learned how one set is contained inside, how one set contains the other, and then we learned how to subtract them also. Now let us see another thing called as Cartesian product. So this is the initiation of relation between two sets. Like if you have two sets, like how they are related. So let me tell you, let us take set A1, 2 and 3, and let us take another set B, A comma B. So the Cartesian product A cross B, it is denoted by A cross B, which will have nothing but the ordered pairs of the numbers. Ordered pair. What is an ordered pair? Ordered pair is a pair of numbers which follow certain order. That is, like I said, okay, 1 you go and sit in the first place and A you go and sit in your second place. So they have to sit there. If they sit the other way around, I'm not going to say that they are the same what I wanted, because 1 comma A is never equal to A comma 1. That is why they are called as ordered pairs. Like order is important, like first and second elements. This is called as the abscissa and this is called as the ordinate. You might be knowing it. So when I say 1 comma A, it should be 1 comma A, it cannot be A comma 1. So I will always say 1 comma A is not equal to A comma 1, and I will say A comma B is not equal to B comma A unless A is equal to B. So we'll talk about that in a while, but now let us see what is the Cartesian product. So 1 is connected, so let me draw the diagram also for you. 1, 2 and 3, and this is A comma B. So 1 is connected to A and 1 will be mapped to B as well, so 1 comma B you get. Right? Then 2 comma A and 2 comma B. So you get 2 comma A and 2 comma B. Instead of all possible mappings we take, this is called as the Cartesian product. And 3 comma A and 3 comma B. So this is called as the Cartesian product of the two sets. Right? Now if I say B cross A, can you guess what would be the elements of the C? This is also a set, and here the elements are not simple numbers, they are the ordered pairs here, right? They are not the numbers, but they are the ordered pairs. Now if I want B cross A, it is A comma 1 and B comma 1 and so on. Like all those numbers will reciprocate, like all the ordered pairs will reverse the order so that you get a B cross A. And it is clearly evident that A cross B is not equal to B cross A. A cross B and B cross A are not equal. Right? So what is Cartesian product? Is nothing but the ordered pairs taken from A and B mapped together like one to the other. Right? Clear. Now, if I take any subset of A cross B, suppose A cross B, I have 1 comma 2, 1 comma 3, 1 comma 4, and 5 comma 2, 5 comma 3, and 5 comma 4. Right? Can you guess what are the sets here? A is nothing but 1 and 5, and B is nothing but 2, 3, 4. Right? Now, if I want to, if I pick a small subset of this, say suppose 1 comma 2, and I take 5 comma 2. I took a subset of this one, right? Like you can say now R is a subset of A cross B. Why I am naming it as R is like this is called as a relation. Any subset of the Cartesian product is called as a relation. And there are several types of relations which we are going to talk about in some time now, right? So any relation is nothing but a subset of A cross B, and A cross B, completely A cross B is also a relation. Like if I take the entire A cross B, that is also a relation. A Cartesian product is also a relation, and any subset of it is also a relation, right? Now let us quickly talk about a few properties of the sets which we have discussed so far. Say suppose I have A union B. What can I say about a relation between set A and A union B? A is definitely a subset of A union B. Yes or no? Yes, because in this we have all the elements from A and from B. So A is definitely a subset of A union B. In the same way, B is also a subset of A union B. And A intersection B is a subset of A. Right? A intersection B is a subset of A. Similarly, B is also, A intersection B is a subset of A. B. So the intersection is subset of those independent sets, and the independent set is a subset of A union B, right? Now if I have A union A, what am I going to get? I'll simply get A, because I'm joining A with A. I'll simply get A. I won't get anything else, right? And if I meet A with A, like I have A and I have to find the intersection of A with itself, I have to join one more circle on the same thing, so you still get the same A again there. And then if I have A union phi, it will be A. Similarly, A intersection phi or A meet phi will be equal to null set, right? And at the same time, if I have A union, the universal set, I'm writing it as mu here, then this will give us the universal set, and A intersection universal set will give us the set A. Clear? And the basic properties of A union B, union and intersection, they are commutative. A union B is equal to B union A. At the same time, A intersection B is equal to B intersection A. Right? These are commutative laws. And then if I have, say complement, we already know complement, right? Like so, null set, what is a null set? So complement of null set is what? Complement of null set is nothing but the universal set minus null set. So from the universal set, I am subtracting nothing, then I will simply get the universal set. So complement of a null set is universal set, and the complement of universal set is simply null set. And if I have a set A and its complement I want is nothing but null set, universal set minus A. And if I want the complement of the complement, I need to do this, and then I get it is equal to A. So A complement, whole complement is again equal to A, the same set you will get, right? Also, this A union, this union is associative. A union B union C is always equal to A union B union C. Similarly, with intersection also it is the same. And union is distributive over addition. So if I am doing A union B intersection C, I will get A union B intersection A union C. Similarly, if you distribute intersection over union, you get the same thing, A intersection B union A intersection C. So the distributive laws hold good in with union and intersection. At the same time, there are something called as De Morgan's laws, which are nothing but using the complements, like A union B whole complement. If I want to find the complement of this, which is nothing but A complement intersection B complement. In the same way, A intersection B whole complement will be equal to A complement union B complement. So to remember it, like to help you remember, when it is union and there is a whole complement, it is like the complement of union changes it to intersection, so it becomes A complement intersection B complement. At the same time, A intersection B whole complement will be equal to A complement union B complement, right? And now how is this subtraction operated on unions and intersections? Say suppose I have A minus B union C to be found. So this is nothing but the difference of A and B intersection the difference of A and C. In the same way, like if I am subtracting the intersection part here, it is nothing but the difference of AB and its union A minus C. So whenever you are operating the minus and the subtraction on union and intersection, they tend to interchange, they tend to change there, right? Now let us now come back to our relations. Like how are these relations defined? Say we already have seen, right, like I have seen a set A with 2 elements, 1, 2, say let us take 3 elements here, and B is a set with 2 elements A comma B. So how many types of relations are possible? See, relation, now recall what is relation. Now see, relation is nothing but the subset of the Cartesian product. So if I do A cross B, I have so many ordered pairs coming, like 1 comma A, 1 comma B, 2 comma A, 6 ordered pairs I get, 2 comma B, 3 comma A and 3 comma B. So how many relations I can find? The relations are nothing but the subsets of this. Subsets of this would be a null set and a set itself, and these all of them, like one of them, picking one of them or various combinations of them, you get, like it will be very tedious to list them all, like it is you know how to write those also. Like suppose I'm defining a relation R1 for example, so 1 comma A and 3 comma A, this is one relation I'm defining. So this way you can figure out so many variations. So the number of relations like this, how many different subsets you can make, is nothing but 2 power m times n. For example, here it is 2 power 3 times 2, which is 2 power 6, which is like 64 relations. You get like 64 different subsets you can write. So we cannot write that for this time now. So you can list it down if you want, and you will find it out by yourself. So when A and B are 2 sets where order of the cardinal number of A is m and cardinal number of B is n, then the number of relations of the set is given by the formula 2 power m times n, right? So now you know what is a relation now, right? Like relation is nothing but you are writing the ordered pairs, picking the ordered pairs 1, 2, 3 A, B, C. As we have seen earlier, you are writing 1 comma A when 1 is mapped to that, and 1 comma B when you see 1 is mapped to B, and 2 comma C when you see this, and 3 comma A when you see that, right? So when these are mapped, this is one relation I'm defining. I'm not writing all the A cross B here, but I'm just writing the relation. This is a relation R1 I'm saying, right? So in this we should know some terms now, like which is called as domain and range. See, the elements which are connected are called as the elements of domain. The elements to which they are connected are called as the elements of range. So this is the range here and this is the domain. So the first element, set of all the first elements, are the abscissa of all these ordered pairs together taken as a set, is called as the domain, and the ordinates of the relation taken together as a set are called as range, right? So the domain is nothing but the first set and range is nothing but the second set. So we know now what exactly is a relation. A relation is nothing but a mapping from domain to range. Now there is something called as identity relation. So types of relations, we are talking about, say, types of relations. say A is a set which has 1, 2, 3, and I have a relation say IA, which is nothing but the ordered pairs of 1, 1, 2, 2, and 3, 3. This is called as an identity relation, like which maps itself, which maps every element to itself, is called as a identity relation. That is nothing but if you see an element A belongs to A, then A must be related to A. See, this is a notation which we use to say that those two are related. Or else you can simply say A comma B belongs to A and A is related to B, then you can simply say A is equal to B. So when A is equal to B, then only it is related. That means if two elements are related, means if there is an ordered pair, then A is equal to B. That means the abscissa must be equal to the ordinate, then it is called as a identity relation. Now let us say A is I'm talking about a relation R, 1, 2, 3, 4 and 5, 6. This is a relation. Now if I write a relation this way, let me name it as R inverse. We're talking about inverse relation, you might have understood by now. So what will this be? 2, 1, 4, 3. We just reverse the domain and codomain, then it is called as the inverse relation. Inverse relation. Now say, suppose I have a set A 1, 2, 3 and a set B A, B and a set C X, Y. Okay, and now I have, okay, let us name it as C, and here I will take Z as well. Now I have 1 is mapped to A, 2 is to, I'm sorry, 1 to B and 2 to A and 3 to C. And then C is mapped to Z, A is mapped to Y and B is mapped to X. Let us name this as relation R1, this as R2. Right? This is A, this is B, this is C. This is called as a composite. See, A is related to B and B is related to C. Now a relation from A to C is also defined, like from, if I take 1 is related to B and B is related to X. So I can directly write 1 is related to X. This is called as the composition of the relations. Now there is something called as a equivalence relation. A relation is called as equivalence relation if it satisfies given conditions, like few conditions. What are those conditions? The relation should be reflexive, then the relation should be symmetric, and then the relation should be transitive. So what is this? Let us talk about it now. It should be reflexive. What is reflexive? Say suppose A is a set and a small element A belongs to A. For every A belongs to A must be related to A itself. Then it is called as a reflexive relation. So A comma A must be present in A. Then it is called as a reflexive relation. For every A belongs to A comma A should belong to the relation, right? Or else you can simply say A is related to A. This is called as a reflexive relation. And the next one is symmetric relation. What is a symmetric relation? Say suppose A comma B belongs to A and A is related to B, then B also should be related to A. For example, if I have A comma B present in the relation, then B comma A also should be present in the relation. Then we call it as a symmetric relation. If it is not happening, then it is called as non-symmetric relation. So a reflexive is A belongs to A, then A comma A belongs to A. For every A belongs to A comma A should be in the relation. And at the same time, if A comma B belongs to A, then B comma A also should be in the relation. Then it is called as a symmetric relation. The third one is transitive. What is transitive relation? If A is related to B. See here, A comma B comma C, these are the three elements in set A. A is related to B and B is related to C. Then A must be related to C. then this is called as a transitive relation. So A is connected to B, B is connected to C, then A should be connected to C, then it is called as transitive relation. And if a relation is satisfying all these three conditions, then it is called as an equivalence relation. A relation is equivalence relation if it satisfies all these three. It is reflexive, symmetric, and transitive. Now we have seen what is a symmetric relation. There is something called as anti-symmetric. For example, A is related to B and B is related to A, then A is equal to B. See, I have A comma B and B comma A both present in the set, right? That's what we discussed just now. Like a relation R is said to be symmetric if A comma B is there, then B comma A also should be there in the set, right? So when these two are there, then it is called as a symmetric relation. But when this is happening, then A and B both become equal, then it is called as an anti-symmetric relation, right? So when a relation is reflexive, anti-symmetric, and transitive, then it is called as a partially ordered set. Okay, this is called as a partially ordered set. When a set is when a relation is reflexive, anti-symmetric, and transitive, then it is called as a partially ordered set, right? So we have learned about sets and relations in this section. Let me see if you have any questions. So we'll discuss. I think you didn't have any questions. I didn't get any of them from you. So we will discuss more on these types of relations and equivalence classes and types of functions, invertible and inverse functions, and composite functions in our next session. Till then, signing off. This is Satish from Toppr.